So, real quick thing about what you're going to see in the homework in chapter 12. They're going to ask you the same stuff about make a scatter plot. You can do it by hand very easily. Yes. Just X, Y points, not a big deal. Just got to pick a good scale, right? Can anyone tell me real quick, if somebody gave me the scale, do you see anything wrong with the scale?
It's not consistent.
Yeah. So the quickest way to make a math teacher cry, besides kick him in the shin, is make a bad scale. This is not a consistent scale. So whatever you see when you plot the points here is not going to be anything meaningful. You guys with me? So make a good scale. Okay. We'll do an example like this in a bit, but we'll do a whole linear regression example later. But in the homework, what you're going to see is you're going to come up with a line of best fit. Let's say that y is the revenue, and x is the number of number of number of ice cream cones sold. Right? And I get something like this, y equals, you can do it, Jeff. This is revenue in hundreds of dollars. And this is number, okay. So let's say I get 0.2x plus, say minus 10. What would negative 10 mean? What's the meaning of that? That's the y-intercept, right? Negative 10 is the y-intercept?
It's where the line crosses the y-axis.
Exactly. So what is true about x at the y-intercept? What value does x have? To find the y-intercept, you make x 0. What does x represent?
Number of ice creams.
Number of ice creams sold. So when I sell no ice creams, no ice cream cones, I actually...
You're down $1,000.
Down $1,000, so $1,000. Yeah, you guys with me so far? So for interpretation of y-intercept, the y-intercept is always 0b. Yes.
Yeah.
When I make x 0, I get whatever number's out by itself. So that's the y-intercept. So how do you interpret every y-intercept in the universe? When the x variable is 0, when you have none of whatever x means, you get this much for whatever y means. So when I have no ice cream cones sold, I will lose 1,000. Negative 10 times 100 is $1,000. So $1,000 is like my overhead. You with me? Like rent or utilities or materials or resources. You guys at all with me? I'm not going to make this a business class because that would suck. You wouldn't learn shit from me because I hate business. Okay. What does the slope mean? Well, we just said slope is the change in y over the change in x, right?
Mm-hmm.
What's the unit on the y's? What's the units on the y?
Y units is revenue in hundreds.
Come back to me. Yeah, it's dollars basically. Hundreds of dollars, yes? So y is hundreds of dollars. Yeah. X is what?
Number of ice
Number
cream.
of ice creams.
Number of ice cream sold. So can anyone interpret the y-intercept? I'm sorry, the slope. We just do y-intercept.
Positive.
It's positive, good, which is good. So for every ice cream I sell, I make 0.2 times 100. I make $20. I'm not sure what kind of ice cream I'm selling.
Sounds
What's in these
premium.
cones?
Italian gelato.
It's,
Yeah,
the real
imported
premium
from a
stuff.
specific city in Italy.
Yeah.
Are you guys with me?
It's from organic cows.
Yeah, it's from the Happiest Cows.
They feed them wine.
Sure, we feed them wine and. Are you guys at all with me? So slope is y over x. So whatever the unit is on the y, whatever the unit is on the x, you just do y over x. You just do this per this to figure out the slope for any situation ever, not just for my class. All right. We'll see how that goes. You gotta try that homework out. So what we're about to get into is, so let me say this. Here's a normal curve, roughly, right? What have we used the normal curve for? Like, what tells me, what would be different between these two? Let's say they have the same mean. What is different between these two? Anything?
Concentration.
Be more specific. What's the thing that is different between these two? The means are the same. Did I not make it extreme enough?
One is normal.
They're both normal.
They're both normal.
Just one is much
Data is less spread out.
less spread out, which means one is smaller for this
Oh,
one.
the standard deviation.
Standard deviation is smaller. So this is sigma 1, sigma 2. Sigma 2 is less than sigma 1. You guys with me? Standard deviation is the number that kind of represents the shape of the normal curve. If sigma small, it's going to be skinny. Sigma big, it's going to be fatter. It's going to be wider. Are you guys with me?
The spread.
Yeah, it's the spread. We know this forever. So what if I want to look at a bunch of samples and how their sample standard deviations are distributed? Will it necessarily have the shape, considering that the standard deviation is normally what determines the shape of the distribution? All right, I really want you guys to think. Everybody agree with me that the standard deviation determines how spread out the shape of this is. Yes? Skinny, fat, whatever. Okay. And how have we used this? Haven't we used this like I would find every sample of size 35 and I would plot their means and that would go into a normal curve. Is everybody with me?
Yes.
How do I know that would be normal? Because that's greater than 30. Okay. Is everybody with me? We've done it with p hats. Every p hat and I can put it into a curve and I can see if n p hat and q hat are bigger than 5, or at least 5, then it's going to be normally distributed. Is everybody with me? Okay. So what if instead of taking a sample and calculating a sample mean or a sample percentage, what if instead I calculate a sample standard deviation? And I do that for every possible sample I take. What the shit is that going to look like? Considering the shape of it is normally very highly dependent on what the standard deviation is. And now instead of plotting a bunch of averages, right? We're 2 years old, we're 87 years old. Instead of plotting a bunch of averages, I'm plotting a bunch of standard deviations. So I don't have like one standard deviation to rule them all. I have a bunch of little standard deviations. What the hell shape is that thing going to be? Well, I'll tell you, it's not going to be normal. It's going to be this guy. Can anyone tell me anything about that?
Skewed to the right.
Skewed. Skewed, right? I'll just get this out now.
It looks skewed left.
Huh?
Why does it look skewed left?
If this was a mound of taffy, where would somebody grab it and pull to make that? Which direction would I pull?
You're opposite.
Hmm?
You're
Right.
opposite.
Which direction would I pull? I don't care. I don't need you. I'm talking here. Which direction would I pull? If it started off looking like this, which side would I pull on it to make this? Which side would I grab on this to make
Right.
this happen?
The left.
You're right.
Alright.
You stretch it.
Oh, you want to stretch it?
That's what's happening. It's like a thing of taffy or bubble gum, whatever works. Where would I tug on it to make it look like this? When I tug on this side?
Yeah.
To make it become nice and long and stretchy on the side? So this is skewed right. Whatever side it looks like somebody grabbed and pulled on, that's the direction it's skewed. Okay, let me stop for a minute. Okay. So let me ask you this. If this is a plot of all the standard deviations, what is the smallest the standard deviation can be? Can it be negative?
No.
Hell no, that wouldn't make any damn sense. 11. So what's the smallest it can be?
Like 0.
0, beautiful. If I had a data set where all the numbers were 3, 3 through 3, 3 through 3, 3, 3, 3, 3 through 3, all of it's 3, what's the spread?
None. There's no spread.
0. Kick ass. So the smallest a standard deviation can be is 0. That's why there's a line right there. That's why it starts at 0. That's the smallest it could possibly be. And then it has this weird ass skewed right shape. We can't get completely into why it's exactly this, but it should make some sense, hopefully, that it's not going to look like this. There's no reason it should look like this. Since the standard deviation is normally what controls what this looks like, it's going to have kind of its own shape. So this is what it looks like. Now, somebody help me out. What was one formula that we use to get z-scores that fall in this shape? Give me any formula we use for the z-score.
X minus mu divided by
Sigma.
yes.
All right, somebody else give me another one. Maybe with some p's. I'll get it started.
P hat minus P over S? No, PQ over sigma. Q over N.
No sigma. Yeah. So when I have p's and q's, I make my own sigma. I don't need anyone to tell it to me. You guys kind of with me? That's one reason we didn't use t-scores for that, because we're always assuming we can make the population standard deviation. We don't need t-scores. Let me stop for a minute. Not a minute. A few seconds. I love you guys. Right, so just to remind you guys, right now we're in the derivation phase. We're talking concept. We're not to the nuts and bolts phase yet. The nuts and bolts are going to be a lot more straightforward. I'm trying to lay the idea down about this weird ass thing. So here is, first off, just like z-scores live in a normal curve, what lives in this curve, they're called chi-square. So the Greek letter chi looks like an X that's had an interesting night, and it's chi-square. The square is a part of the symbol. You cannot square root it away. You guys with me? The square is, the symbol is not complete until you write the 2. You guys with me? So this is called the chi-square distribution. There are multiple formulas for chi-square in exactly the same damn way there are multiple formulas for z. Are you guys all with me? Don't every formula for z, don't they fit in, as long as it's actually normal, don't they fit into the shape?
Mm-hmm.
Good. So I have a shape that multiple formulas lead to z-scores that fit into that shape. I have a shape that multiple formulas for chi-square fit into that shape. So here's one formula. Here's the most basic formula that we might not actually get to use too much, but oh well. The most basic formula for chi-square is this one. While I was talking, I was like, oh shit, do I remember it? Yes, I do, okay. Can anyone identify it? Of course you can, everybody could. What is n minus 1?
Degrees of freedom.
Degrees of freedom. S, of course, is sample standard deviation, and sigma is population standard deviation. So real quick, I want to, again, when I'm in the derivation phase, it's not, this is a little side note. I'm gonna compare these two. You don't necessarily have to understand every damn thing I'm talking about, but I at least have to try to get some of the concept across. And then we're gonna get into the nuts and bolts of what it's gonna look like for you. Sorry, I got Gorilla Glass. Gorilla Glass. It's the unbreakable shit. Yeah. No, not really. Okay.
Thank you.
Huh?
Thank you. What were you?
Oh yeah, I'm sorry. I brought it up for a reason and then I forgot to put it down. Just whenever that happens, let me know. So what I want to say is this. Do you see how z-score compares a data point with the mean? Yes? And we've known this forever. It has my data point. In fact, let me write the other one. It's a little more specific to what we're doing. This one is a variation on that, yes? That's the one I use when I have a sample, when I have to change the standard deviation. You with me?
Mm-hmm.
So it's our mean compared to what we know the real mean is divided by the spread. We've been doing that for a while, yes? Do you see how this one, I'm going to take every sample I take, I put its standard deviation here, times the degrees of freedom divided by the population standard deviation. That's how I make a chi-square. It's still a relationship between our data and the population number. Just the same way if I make a z-score, it's a relationship between our data and the population number.
Wait, so this time you're just comparing standard deviation?
Totally. I like it.
It's gonna mess me up. I'm gonna see that square and be like, I need a square root.
I know. It sucks. It's too bad. Okay. So this formula, again, just to remember how I did this when we went to Alternate Universe, Florida. I said, I talked to one group and they tell me, and then I talk to another group and then I build this picture, yes? Okay, same way I could do here. I could go talk to a group of people, they figure out the standard deviation of their ages, and then I plot it. And then I talk to another group, figure out standard deviations, and then I calculate this, and I plot it, and I plot it, and plot it, and eventually I get this picture. If I do every single group of size whatever, it will end up looking like this. Okay, maybe. You're all like, okay, dude. So it shouldn't be too surprising then. We have a chart for values and how they flow in this image. I've also got our last new chart that talks about how things flow in this. The new thing with this is, number one, is this symmetric?
No.
Nope. Number two, can this go negative?
No.
Nope. Number three, this actually never ends. I can get really big really quick. It's crazy. So you'll see what I mean here in a minute.
So it's like t-scores can't be negative.
No, t-scores can be negative all day. Yeah, whole total. Yeah. Just means they're below the mean, just like z-scores. Yeah.
Oh
All right. Wait, I forgot where I was going. Oh, yeah. Okay. Here is another situation. Okay. So this is the most kind of fundamental formula, but there are other formulas that create chi-squares that live in this shape that I can then look up on the chart and get areas and do stuff, get probabilities. It's going to feel a lot like before. We just have different formulas we're using and a different chart. The other situation that we're going to focus on today is this kind of situation. Let's say that, what was the example I gave? That's true. All right. Sure. Let's do this one. Okay. I'll do this to you in a minute. All right. So let's do every stats teacher's fall back to is a bag of frickin' M&Ms. You with me? Now, unfortunately, you might be looking around. I don't have any M&Ms for you. I'm sorry, it's too bad. So if you didn't buy your own, too bad. But theoretically, if I get a bag of M&Ms and I pour it out, and I somehow have the willpower to not eat any of them immediately, so I would not do this experiment well. Just get in my mouth. And I want to know, what's the distribution of the colors of M&Ms? I want to see, is it truly uniformly distributed? You guys kind of with me? All right, let me see if I'm up on the colors of M&Ms. I know if you go to the M&M store, you can get all kinds of neat shit, but I'm talking about a standard bag of frickin' M&Ms. It's like the 6-color crayon box or whatever, right? Not the one with the sharpener and all kind of stuff. So let's say we have brown M&Ms, yellow. Do we have yellow M&Ms in here?
Yeah. Red, green,
Red, blue, orange, yes?
Yep.
Green.
Yep.
And that's it.
Good. All right.
There's purple.
Is there purple?
Not
Not
the
a
basic
regular
one.
pack.
Not a regular pack.
I've never seen it.
Yeah, you got the kind with the eraser on. Okay, I'm sorry. The sharpener on there.
You got the fancy brand.
So these are the categories of possible colors. Let's see, leave this one blank, and let's put, this is going to be my expected. So if I got a bag of 42 M&Ms, let's say we get 42 M&Ms. And I think they should be uniformly distributed. What would that mean?
Every single color will have the same number of M&Ms.
Yeah. How many colors do I have up there?
6.
42 total M&Ms. So if I'm expecting it to be uniformly distributed for each one to have the same number, how many should each of them have? 7. Right, 42 divided by 7. 6, I love it. I'm sorry, other way around. 42 divided by 6, 7. So I would expect, if I'm thinking it's going to be uniform, I can put down 7. I expect there to be 7 of each. Now, real quick, even if across a lot of bags it was uniformly distributed, could each bag have its own variability based on kind of like what got dumped into it as it went through the whole machinery? You guys kind of with me? So, just like a hypothesis test builds in the fact that I already know my sample is going to be different. So in order to pass that hypothesis test, I don't just have to be different, I have to be very different. Yes? I have to be so different, I'm like, holy shit, it's probably less or whatever. Are you guys kind of with me? That's the whole idea there. Same thing's going to happen here. So let's say I actually open the sucker up, and I find that there are 5 brown, 6 yellow, 5 red, 10 blue, 9 orange, and 7 green. So I want to see, is this enough evidence to show that across all bags of M&Ms, they're not uniformly distributed? This one bag is not uniformly distributed, correct? But I'm talking about across all the bags. Do they kind of average out to be uniformly distributed? Are you guys at all with me? I want to see if this is enough evidence that it's far away from what I expect. Is it what I expected exactly?
No.
Obviously not. But that's not good enough. We know this from hypothesis tests. We got to keep going. We want to see, is it different enough? So this one we call observed. So we have what we observe, we have what we expect. So right away, this is going to be really silly. Just go with me. How did you know they were different?
Because these numbers are not 7.
Totally. So how different were the browns, for example? 2. I love it. So you just say 2. So does it make sense that at some point I want to do observed minus expected? You guys kind of with me? In fact, let me see if you guys remember way back. Remember way back when we did standard deviation and we did x minus the mean, but when we added those up, it came out to be 0 all the damn time.
Yeah.
What did we have to do to make sure that didn't happen? Does anyone remember? Squared it so that always came a positive, and the last thing we did was we square rooted it.
Oh,
Okay.
that was to calculate standard deviation.
Calculate standard deviation way back in the day, before I allowed you to do one of our stats. Yes?
We're not going to do that, right?
No, don't worry.
Thank you.
But that's just to explain what I do here. So I'm not just going to do observed minus expected to see how different they are. I'm going to square it at the same time. For the same reason. I'm going to square it so that the answer, so when I add them up, it doesn't just always come out to be 0, or else I can't tell anything. So help me out. 5 minus 7 is 2 squared is
4.
6 minus 7 is 1 squared is 1. 5 minus 7 squared 4 again. 10 minus 7 is 3 squared is 9. 9 minus 7 is 2 squared is 4. 7 minus 7 squared is 0. Okay. This feels familiar, maybe,
Do we
But-
add them up?
a different way. Not quite yet. So let me ask you this. If you expected somebody to have 7, let me see how I say this, 7 left-handed desks, and they only have 5. Could that be a problem? Yeah. It's not like that could be a big problem. That's like a decent number, a percentage of people. That might not be the best example we think. If I expected to get paid $7 and they paid me 5,
That's a problem.
that's a problem. What if I expect to get paid $7,000 and they paid me $6,998?
Pretty freaking close.
It's pretty close, right? To be honest, knowing me, that's a number.
Really?
Oh, hell
No,
no.
the government
It's
will
a
but-
dollar.
government will
but
get mad if you miss taxes
Will
by
it
a penny.
be that relatively big of a deal?
Not comparatively, no.
No, somebody's like, I'll give you $7 million, and they give me $2 less than that. I don't give a shit. Keep it. That's your tip for having to carry all that money to me. All right, you guys kind of with me? So what I'm saying is, I need to know the relative strength of the difference between these two things. So I'm going to take my observed minus expected, and I'm going to divide it by the expected. That's kind of like a relative amount that it's off by. I need this to make sense. So if I said, oh, I'm off by $1, and what I'm buying is a car, are they going to care? No.
No.
If I'm off by $1 and what I'm buying is a Kit Kat,
They're gonna be upset.
they're going to care. If I'm off by a penny and what I'm buying is a Kit Kat, they're not going to care. Because again, the relative size of how much I'm off by is small with a Kit Kat or a car, but $1, that's big for a Kit Kat. Are you guys kind of with me? The relative size of how far I'm off. I need this to make sense, okay?
Makes sense.
Thank you. So let's try this. So can somebody help me out?
Oh.
What is 4 divided by 7?
Let's say 4
Yeah,
seconds.
571 something. 1 divided by 7 is 0.1428, I think.
Yeah.
143. So 4 divided by 7 again is 571. 9 divided by 7 is 1.285.
286.
1.29. 4 divided by 7 is still 0.571. And 0 divided by 7 is 0. It's crazy. So let me do this while, does anyone notice this kind of problem is screaming to be put in the frickin' lists? Anybody? Or do you guys,
No.
well, it is, too bad.
I don't imagine they put the whole thing into the lists, right? Because we've already done the calculations, so you're not putting 4 columns,
There's
right?
only we use like 20 things to put in there.
I agree.
One of those messed up.
It would make more sense, this is not that bad, but if I gave you a lot more stuff, then you want to put it in the list. So just in case you want to see this in here, and even if you don't, I'm still going to do it.
That was it, me, that was me.
Alright, so I'm going to put in there my observed, my expected. I want to make L3, I want to make it L1 minus L2, the whole thing squared. So
Wait,
I'm going
wait,
to do,
wait,
You went
You
one
put
from
one
L2.
less.
what'd I do?
You need to subtract 1 from L2.
Oh, I see, okay. I want to look crazy with my
You need
sevens.
to add a 5 between 6 and 10. You
Yeah.
missed one.
Sorry?
You missed
You
a
missed a
5
5
between
and
6
now
and
one.
10.
I missed something between?
God bless you.
Bless you. I tell you what, kids. Get old, kicks ass.
You're
5,
good
6,
doing it.
5, I see, okay. 10, 9, no, not 97, Jeff. 97, and then I can put the 7 back in.
Right.
Thank you, youngsters. Alright. So then I want observed minus expected squared. So it'll be L1 is my observed. I can't look at you. L2 is my expected, and then I square that. Everybody with me?
Yes.
Shlabam. That looks familiar.
I'm gonna say you need to save your Sam.
And then I want L4 to be L3
Divided by
divided by
L2.
L2. Schlapow. Kick ass. And then this is what I add up. So now, the same way we have multiple z-score formulas. We have multiple chi-squares. So another iteration of chi-square is the sum of O minus E squared over E.
Move it up.
So just add up this last column. So in the calculator, I could just do list, math, sum, L4, I think. Okay. And I get 3 point, where did it say? 143, let's say. So you guys with me so far? Okay, right now we don't know what the shit this means. You with me? We don't know what the shit this means. If the sample would have been exactly what I expected, what would this come out to be?
0.
Of course, if all of these were 7s, all these would be 0s, all this would be 0, this would have been 0 perfectly, correct? Okay, so in the chi-square shape, there's 0, correct? So this, anything close to this, is going to be where I would expect it to be if the difference really is 0. So to show evidence that it's different, that it isn't what I expect, I've got to be out here. Which means I have to find a chi-square for my rejection region.
That'd be 3.143.
No. This is like z star.
Oh, okay.
So what we haven't done yet, because we haven't been able to, is to look up my rejection region number from this chart. Okay. Yes. I told you before, this is our last new chart. Basically out of time for new charts, so too bad.
Does this only work for you?
Huh?
Does it only work for you?
That was L3.
No. There's one more category of
Yeah.
type of thing we're gonna see. So I'll do an example like that too.
Oh, this is fun.
I like that.
It's better than 12. No, 12 is stupid.
Scatter charts aren't stupid. I use them to
That's-
predict
you
the
should
next
really-
recession.
It's your opinion though.
I do.
Figure that out. There's one for 4. All right, guys. So, first thing is going to be a little weird for goodness. I'm sorry. Well, yeah, I might as well tell you what the name of this is. We were trying to see if what we saw fit with what we expected. Does that make sense to say it that way? We want to see if what we saw, what we observed, fits with what we expect. So this is called a goodness of fit test. That's not my name, that's the name for this test. This whole thing we're just doing right now is a goodness of fit test. You calculate chi-squared by filling in this table and adding at the end. You calculate the rejection region. You ready? I'm going to say, let's just say alpha is 0.05, just to be nice and traditional.
Are we always going to be given alpha?
You have to, yes. Well, this book, I don't know. If the book doesn't give it to you, you know it's 0.05. So how do you read this crazy ass thing? Okay, here's what you're going to love. Degrees of freedom is not 41. For a goodness of fit test, N is the number of categories. And to be really honest, if you look in the book, you're going to love this shit. How do you spell categories?
C.
K, that's right. So degrees of freedom is K
No.
minus 1.
It's a C.
I know it's.
Oh. Okay, finally.
I love how concerned you looked.
Well, 'cause if you-
I know you teach math.
The way that you were like just so.
I know. I'm good at it. So I always find this hilarious. I mean, they use the letter K for categories, which is just beautifully funny to me. But
Also be 5.
yes, good. So in this case, our degrees of freedom will be 5 because we have 6 categories minus 1, 5. Now, the other thing you have to realize, okay, this chart. What's a z-score chart? When you look up a z-score, where's the area that you find?
To the left of the
To the left. Notice what this says.
area. To the left.
Yeah. So if I want alpha to be 0.05, where will alpha be on this
That makes
picture?
sense.
In the tail, 11. So this is alpha. So 0.05 is my alpha, so I'm going to look at 0.05. That's to the right of the critical value. So let me go back again. This would mean what? What is this right here? What's the value right there?
0.
0. What would that mean if I got a chi-square of 0 right here?
That we have everything we expected.
Everything we expect. So could it be evidence against
No.
this being uniform? No. So not only do I have to be different than exactly the same, I have to be different enough. And that's what this number tells me. The same thing as before. So what do you get when you look at 0.05? Degrees of freedom is 5. I get 11.071. Is that cool?
So
You guys
that's
all right?
the area to the right.
No, that is the chi-square score. That is the benchmark. That's kind of like looking up your rejection region z-score, like 2.576. You say if z star is greater than 2.5. I'm
Also,
making fun
now
of all of
it's
us. You're
greater
all
than
nerds.
this
You're a nerd with me. We're all together. So it's just like looking up my z for my rejection region. If I get 2.576, it has to be greater than 2.576 to reject the null, blah, blah, blah. In this case, I'm not going to make you do a full-blown hypothesis test. We're just going to go right to the heart of the problem. That's how far we had to get to show evidence that the whole population is not uniform. Did we make it far enough? How far did we make it?
No, we didn't. 3.1.
Our chi-score is 3.143, so we made it like right there. Nowhere near far enough. So did we find evidence that the population is not uniformly distributed? No. We did not find evidence. Population is not uniformly distributed. Just so you know, English is finally caught up with the rest of us, and it's fine with double negatives. They were in the dark ages for a long time, but they now understand double negatives are fine. Yes?
Where did you get the 5 for the degrees of freedom again?
How many categories are there? Brown, yellow, red, blue, orange, green.
Oh, 6.
6 minus 1?
Okay.
5.
I got
So
it.
that's, it's silly that they have a K there. That's kind of funny, but I always remember it's like category spelled wrong. Which I totally knew. Okay. So let me give you this. This is actually what we just did, just with much better writing and a better picture. And then we're going to do number 2 together. It's an example of the other kind that we can see.
What was your conclusion, Professor? No, we did not find evidence.
That it's not uniformly distributed. So we're always trying to find evidence against it being what we expect. So we don't make it far enough away, we did not find evidence against what we expected.
We did not find evidence.
That is not uniformly distributed.
This is so fun.
Does that mean we can conclude that it's uniformly distributed?
No.
Nope. Just like being not guilty does not mean you're innocent.
It's okay, OJ is facing different type of judgment now. He doesn't. Before we got started class. Gets me
So this is the example we just did, just written much nicer. Look how well you can read that.
If you want
No, I just wanted to make sure.
You don't have to use formal language. You can use exactly what I just said a moment ago. I'm not going to make a full hypothesis test out of this. I think I put you through that enough.
On the bottom, I might be verbally
Some of you guys might say too much, but I'll say just the right amount.
I'm hungry.
So here is the, how you guys doing so far? This is very freaky. By the way, I do want to say one thing. Let me see if even I remember this real quick. Yes, okay. Can somebody look at degrees of freedom of 1? Can somebody really quickly take the square root of 2.706? Just cause.
What did you say?
Take the square. See this 2.706 right there?
1.6.
Rounded to 3 places.
1.645.
1.645. Does that sound familiar to anybody? 1.645?
That's a Z-score of 9.
Totally.
Is it actually?
Yes. Let me see ahead of time.
I've done it too many times.
Doesn't quite work. Oh, it's 3.841 here. Where'd your glasses go? I don't know. Do the square root of 3.841.
One 1.96.
1.96.
1.967,
So, what the reality is, this is not going to come up a lot. This is not going to come up more than right now, okay? But I need to say this, just to make a complete idea. What the chi-square distribution really is, and the reason it has a square on it, a fixed, that you cannot remove, is because it takes the z-score, for degrees of freedom of 1, it takes, oh my god, pretend like it's a normal curve. Holy shit, Jeff, I can't stand. It takes a normal curve, and it folds it on itself. So, if this is 5% and this is 5%, isn't that 90% confidence interval?
Yep.
Yes? Isn't that 1.645, like Bessie said? So if I fold this on itself, that 5% goes with that 5%, which makes it 10%. And then what happens is these z-scores end up multiplying by each other.
Mhm.
So you square them. Now, things get exceptionally weirder as the degrees of freedom goes up. That doesn't hold. In fact, you guys notice something? I mean, if you let the degree of freedom go up, what's happening? Look at this. Look at that. Just days upon this.
Exponential
It's
increase.
crazy. It's crazy. Okay. I like it. Hey, Mikey. Okay. Okay. Let me see. Was there something else I wanted to say? No. This peak, one last thing I want to say in general. This peak right here is roughly around n minus 1. So, do you notice like 7 is between these two?
Mm-hmm.
7's in the middle somewhere. It's going to be right near the peak. Anytime you go down somewhere, it's going to be right in between. 20 is right in between these two. Okay, enough of that. So let's look back at this. Let's do number 2 together here. So one way I can give you how to fill in the expected slot is to say, I expect it to be uniform. If it's going to be uniform, I take the total divided by how many categories. They each get the same amount. Yes? You guys with me?
Wait, say that again?
One way I can create a goodness of fit test is to say we expect it to be uniformly distributed,
Oh, okay.
which means I'm going to put the same number in each of these, which means I take the total divided by how many categories. So I just distribute it evenly. In fact, you might even say distribute it uniformly. Another way to kind of tell you what to put here where it's expected is to give you the percentages I expect. So, here's the blood cholesterol level for the general population. 20% have less than 130, so forth. Are you guys with me? We go to this little secluded area. I like to think it's like a little island. We find a group of 500 people living on this island eating a certain diet, right? This makes me think about like the Mediterranean diet. Everybody started just pouring olive oil on. So Americans continue to eat our normal shit. We just poured olive oil on. They're skinny. Must be the olive oil. So we just poured olive oil in there. I don't know if you guys, this is back in the 70s, 80s, I think. I was young, thankfully. I'm not that crazy old. You guys kind of with me? So often we focus on the wrong thing, right? But we notice they have low cholesterol. They're healthier. People that live in the Mediterranean, and we all focus, they all use olive oil. Oh my God. And that's when people just started using olive oil like crazy. While we're eating our Big Macs, we're eating French fries that were baked in olive oil. I'm healthy. Now, don't get me wrong. I eat frickin' Big Macs every now and again. Not a ton, because I used to work at McDonald's. And that's all you gotta do to not eat there very often. But, all that aside. So we get there, and I'm curious if they have a different, we kind of notice they're healthier, they seem skinnier, they seem all this kind of stuff. We're like, all right, what's going on here? So let's see, their cholesterol level, let's see how different that is. So the observed you just fill in, correct? So I told us that 111 have a level below 130. So of course lower is better. 184 between 140 and 200. Did I say 140? I don't know why I say 140 up there and 130 down here, but too bad for me. 137 between 200 and 240. And then of course I do this evil thing. I think I say the rest.
68.
Yeah. 68, thank you. So that makes a total of
500.
500, okay. My God, both of my pens, Jeebus, really?
You should use a pencil.
Okay.
I'll leave it on there. You gotta throw it away so you don't use it again.
What's that?
The pen, it's dead. Just chuck it.
Oh, sure. Now, to get the expected, I was very nice, and I put this down here, which I should not have, but it should kind of make sense. We expect 20% of any group to have less than 130. That's what we expect, or at least if they're going to follow the same pattern as the general population, we expect them to have 20% to have less than 130. And we talk to 500 people. So of course, how many would we expect to have less than 130? 20% of 500 is
100.
100. I expect to have 30% between 130 and 200. 150. 35%.
No.
75.
175, yeah.
175.
75. And then you can double check yourself, make sure these add up to be 500, just to make sure you didn't multiply something wrong. It does. So again, I want to make sure you understand. Both of these problems are asking the same question. I have an expectation, I have observations. I want to see if the observations are different enough from the expectation to go, holy shit, there's something generally different. So then here we have expectations, we have observations. I can see they're different, but are they different enough to show that the general population, because it's only, well, I said a group of 500 people, Jeff. Damn it. And there's more people in this area, so it's not the whole population. That'd be kind of crazy. So somebody help me out. We could do it in the calculator, but this isn't that much. 111 minus 100 is 11. 11 squared is
121.
121.
1156.
Hold up. 184 minus 150 is 34, and then you square it.
1156.
1156. Sounds about right. 137 minus 175 is negative 38. And then you square that.
1444.
1444? Sounds about right. And then 68 minus 75 is negative 7 squared is
49.
41. You guys with me? And again, you can do it in the calculator if you want to. Well, you know. I would. But what I mean is you can do the lists if you want to. You don't have to. Now this is going to get a little ugly over here, so you might want to know. The first one's not too bad. 121 divided by 100, you just move the decimal back twice. 1156 divided by 150 is a little more involved.
How many
You
decimal
can do it, you
places?
can do it.
How many decimal
No, I don't want to. Huh?
Really? This means you can't do it.
How many
Yeah, I
decimal
can't do it.
places?
I'll say I can't do it. It's fine. I can live with that. Sorry?
How many decimal places?
If you do it in the calculator, you don't have to do any, but do like 3 at least.
7.707.
707? Okay.
8.251. And 0.653.
Okay. And if you add that all up,
17.821.
17.821?
Yep.
Okay. We're going to stop for a minute. So the main thing that could be different between two good as a fit tests is how you fill this column in. Up here, they told me it's uniform. I just put all the same numbers so I can do it based on how many total there are, right? Down here, they told me exactly the percentage I expect in each spot, so then I can calculate in each spot how much do I expect. Then the work I do is always the same, yes? So here's my chi-square. This is like my chi-square star, if you want to call it that. It's like my z-star. So when I say 0.01, level of significance, that's alpha. So what's the chi-square going to be? What's my degrees of freedom?
3.
Yeah, holy shit, that's a weird-ass distribution. Yeah, I got 4 categories, so degrees of freedom is 4 minus 1 is 3. My alpha is 0.01. Don't say anything, just look it up. Don't say anything. See if you can find the chi-square score. Let's see. Did I turn you back on? Yes. Give this thing a chance. It's definitely warming up.
3. Is there a differentiation between the score that we, like what they're called, the score that we find on the chart versus the score that we just calculated? Like which one of them is considered chi-square? Is
Not
that
really.
called?
That's why I created the star
Yeah.
notation.
Okay.
The
Also,
book
this is-
uses Z alpha over 2,
Ew.
which is dumb, but you know,
Why?
so it's a way to,
Wait, what's that number called? Chi-square?
yeah, this is the chi-square. So these are chi-squares. So what did we get? Sorry. 0.01. Degrees of freedom was, I
3.
already forgot 3. So 11.345. And so we're at 17. So did we find evidence that they have different
Yes.
blood cholesterol levels than we
Yeah.
expected? Yes. We have found evidence. Cholesterol levels are different, but let's be more specific. We know they're different, but can you tell me if they're better or worse?
They're worse.
The lower ones, I want more to be here than I expect. Was there more at the lower levels of cholesterol than I expected?
Yes.
Oh.
And the higher ones, I want less to be here than I expected. Was there less with high cholesterol than I expected? Yes. So did we find evidence that they're better than the general population in terms of blood cholesterol?
Yeah.
Yes. So we found evidence cholesterol levels are better here. So then we start to go, okay, is it really in their diet? Do they have like a certain nut off of a tree that they put in everything and it's got these properties that we don't know about because we don't have that tree? Or is it because they freaking walk everywhere?
Yeah, they don't have cars, they have canoes.
Yeah. Or is it genetics? Is it just they are born with high metabolisms or whatever? They have natural ability to scrub their bodies of cholesterol, whatever. We don't freaking know. All we know from this is there does appear to be differences between their cholesterol and the general population. In fact, theirs is better. So then we can do deeper dives into each of the possibilities instead of experiments. Are you guys? We won't just rush and go, it's got to be the nut off that tree. Just everybody starts adding it to everything, right?
America's,
Dr. Oz over here.
Yeah, pretty
you're,
much.
you're in
Shave it on top of your carne asada fries.
You're a stats professor. You might be interested to know that hell, America made a cartoon about it, and we found out 40, 50 years later that spinach is not nearly as healthy for you as we thought with its iron content because the original researcher misplaced the decimal. So
Oh,
it was less
yeah.
healthy by a factor of 10.
Yeah, it's still good, but it's not like crazy good.
There's a reason we're like
Popeye was
yeah.
white based on reality. Yeah.
It's not Popeye good.
There's a reason we're like number 20 in math on the world stage. We suck.
Yeah, wait.
No offense.
No, yeah, well, what can we do?
Great.
Doing everything.
Nothing stupidly overpowered.
Yeah.
Okay. You guys come with me. Yeah, he beats the Tama to death battle. If you're curious. I don't know. All right, so that's that. So, what I want to do now, on the other side of this paper, why don't you guys do number 3 first, since we just did chi-square stuff, and then I want you to do number 1, and then when everyone's done with those, we'll call it a day after we go over them. So do number 3 here first, because we just did these. So do number 3 first. Give my camera a break. Let's see.
Could it be we failed to, or we did not find?
Is it supposed to mean that someone pressed on the dice?
I don't think we found it.
Let's find out. Let's see. Did you guys get these numbers?
Yes.
Yes.
Yep.
Yes.
Jeff.
Doesn't mean that they didn't mess with it.
God.
We don't know yet.
There's numbers.
Let's find out. One.
Okay. So there's one that was really far off, yes?
Yeah.
So the real question is, it's not impossible. It is not impossible to take a die, roll it 120 times, and get nothing but sixes. That is not impossible. That is freaky as shit. The probability of that happening, stupid small.
I'm taking you to Vegas.
But it is not impossible. Yeah. You're like, oh man, I used it all up. Is everybody with me so far? You guys okay out there? Okay. I like the way some people are looking around like, you guys okay? So this one, now, so this is L3, L1, L2, L3. I don't have to put this in there because it doesn't really come into play, right? L4 is going to be L3 divided by, now be careful, in this case, for whatever reason, I put this in L1. I almost always put my expected in L2 just to keep things standard, but for some reason past Jeff put that there. Just make sure that you're dividing by the expected wherever it is. So these numbers look familiar. Is that what you guys got, those numbers here?
Yep.
Yes? Okay. 1.25, blah, 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 blah. So if I add them up, second stat, math, sum, list 4, I get 8.4. How's that sound?
Yeah.
Yes. My name is Jeff. Alright, so that is like our chi-square star. You can call it that if you want to. Now I want to use my alpha to figure out where the benchmark was. What's my degrees of freedom? 5. And my alpha is 0.05. I think we had the same one earlier, right?
Yep.
11.071. So you start to see some numbers over and over again. Of course you do. Sort of like the 1645 and the 2.576. You're going to see some numbers over and over again. Did we make it far enough away? No! We did not find enough evidence that this die goes against the expected. So sure, we got a lot more 6s than we expected, but not so much that it went outside the realm of variability. I'm going to get more of some and less of others, just by pure happenstance. That doesn't automatically mean the die has been tampered with. Now, could the die have been tampered with? Shit, yeah, totally. This is just like us, we found the die not guilty of being tampered with. It might be guilty as shit. But the evidence just wasn't strong enough. Are you guys with me? So this is why people either misuse statistics or they don't trust it at all. So the truth is in the middle somewhere. I don't know. I don't have enough evidence. I don't know everything. So the best I could do is say we haven't seen enough evidence to say it's been tampered with. Right? Okay, maybe. Now, if the person that's using it, if we know they've cheated before, that adds to the circumstantial evidence. You with me? But that's beyond a statistical study. Okay, maybe. Maybe? Okay. How do you guys feel? That's not as bad, yes? I just wanted to give you a break from new charts. I thought if I gave you another new chart immediately, there might be a rebellion. But it really isn't that bad. This really isn't that bad. So let's do this. Let's do this problem. We'll call it a day then. And then on Wednesday we'll have the quiz and I'll have the practice final. And we'll look at the rest of chapter 12. Chapter 11, sorry. Okay, so go for it. Do that problem there. This is from 5 years ago now. Back in the day, the pre-craziness days.
Pre-COVID days.
Yeah. We were so innocent, naive.
A lot of C's.
Mm-hmm. If anybody needs it, I have the handout from the linear correlation. If you weren't here when we did the linear correlation stuff, on the back it's got the instructions. So, oh yeah, if you need a calculator also, we could do that. Yeah. So if you're doing homework and you don't have one of the multitude of worksheets I've given you as you're sitting next to you while you're doing your homework, you don't make sense to me. That's one reason why I give you so many freaking worksheets, is so you can have it sitting next to you as you do your homework.